Okay, here is kind of a picture of the universe as I imagine it right now. Um, I'm going to pull this over so you can see these numbers. Actually, I should move the whole screen. Okay. Um, the, uh, the values here correspond to Hubble's constants. This Hubble's constant of 67.4 and this Hubble constant of 71.4 kind of correspond to the blue dots here. All of these align with 65, 67, or 68, somewhere between 67 and 68. All of these align with somewhere around 72, 73, 70, 72, 73, 74, 75, whatever. Yeah, 72, 73, 74. Okay. Anyway, you got these two different groups, and basically these two different groups come from two different data sets. Let me just credit Ethan Slegel with this article. So I want to talk about things in terms of him because he refers to himself sometimes in this article. So Ethan. Hello, Ethan. So I want to credit Ethan with this important distinction. Ethan says that there is an early relic method, which includes using the light from the cosmic microwave background. I don't know if it actually does. I'm not sure how it does, but that would be the cosmic Cmbr is definitely an early relic. But then he says, you take something that occurred early on in the history of the universe where the physics is well known, and you measure the light signals from from where that information is encoded to the present. Now, the only thing that he actually lists in this description is the cosmic microwave background radiation. But then what he actually draws a picture of here is all of this, and I think this is the area where he is actually getting this number from the galaxies hosting Cepheids and Type 1a supernovae. This is where he's getting that data. The 67 kilometers per megaparsec comes from this data here. And then, for the nearest objects, we can measure individual stars, such as Cepheids, RR Lyrae stars, stars at the tip of the red giant branch, detached eclipsing binaries, or masers. And in this region, then, the nearest objects, you get a 67 kilometers per megaparsec. Okay, so let me just say, I am saying something different than Ethan is. Ethan says that the 67 kilometers per megaparsec comes from here, and the 72 to 74 kilometers per second comes from all this. But I'm saying the 67 kilometers per second comes from here, per megaparsecs, and the 72 kilometers per megaparsec per second comes from just this inner circle here. Now, I'll acknowledge part of the reason that I make this argument is out of ignorance, because I have knowledge of how to obtain the Hubble parameter for every star and galaxy in this region, and for every star and galaxy and supernova in this region. What you do is you figure out what is the magnitude versus your expectations, and what is the distance versus your expectations. Or I'm sorry, the redshift versus your expectations. So you take these two data points, the magnitude and the redshift, and you can calculate how far away it must be, and you can calculate what its velocity must be. And through those two things, you can figure out what the Hubble constant for that particular um, object is. Now, as far as figuring out what is the Hubble constant for the cosmic microwave background radiation, I just have no idea how. Let's see, where did he say that? He says that it includes the using light from the cosmic microwave background, leveraging the growth of large-scale structure in the universe, including the imprint of baryon acoustic oscillations, and through the abundances of the light elements left over from the Big Bang. Now, that, to me, sounds like complete word salad. It has there's absolutely nothing there that I could find any kind of mathematical meaning to. It there are so many assumptions um, regarding, okay, you're looking at the CMBR and you're seeing baryon acoustic oscillations. How do you know that you're seeing the baryon acoustic oscillations? Abundances of light elements. Okay, so you're seeing the abundance of light elements from the CMBR. Did you are you seeing some kind of um, evidence of absorption lines in the CMBR? Um, you seeing hydrogen and helium absorption lines or something? I just don't know what they're using there um, to see their early relics. As a matter, okay, actually, in the picture, it it actually says distant galaxies in the expanding universe hosting type 1a supernova. So this is actually essentially the same as this, galaxies hosting Cepheids in type 1a supernova. So this contains type 1a supernova, and this also contains type 1a supernova. So it's just that this what this excludes is the Cepheids, because the Cepheids are not very bright compared to the type 1a supernova. So actually in this diagram, okay, they do definitely have what I'm looking for. In the text, he doesn't mention the type 1a supernovae, but in the diagram, he does have the type 1a supernovae drawn there. So, what else? Okay, he mentions this thing about the initial value of Hubble's constant having an uncertainty of about 10%. So, let's call it 7? Anyway, we'll call it, actually, let's call it 8, because on Wikipedia's page about Hubble Space Telescope Key Project, it says the project established the most precise optical determination consistent with a measurement of Hubble's constant based on Sunyaev-Zeldovich effect observations of many galaxy clusters having a similar accuracy. So essentially they got numbers between 72 minus 8, which is 64 kilometers per second per megaparsec, and 80 kilometers per second per megaparsec. So in other words, they were finding what does that mean? What does that error mean? They're actually, what they're doing is they're taking a look at every example of these galaxy clusters. What is it? Oh, wow. It is a spectral distortion of the cosmic microwave background radiation through inverse Compton scattering by high-energy electrons in galaxy clusters. It can be divided into 3 different types: thermal effects, kinematic effects, and polarizations. The thermal effects is where the CMB photons interact with the electrons. Kinematic effects, and kinematic effects, a second-order effect where the CMB photons interact with electrons that have high energies due to their bulk motion. and then polarization. And let's see. Okay, so here's something. The kinematic Sunyaev-Zeldovich effect is caused when a galaxy is moving relative to the Hubble flow. How fascinating. Okay, so we are going to announce that these galaxies that display the kinematic Sunyaev-Zeldovich effect are outliers. They are not in the Hubble flow. So, wow, we're just going to go ahead and say it right out loud. If you get if you have a non-zero kinematic Sunyaev-Zeldovich effect, that means that treating this galaxy as though it is a member of the Hubble flow is invalid. It's not a member of the Hubble flow. So if you are at all adding or subtracting this quantity to your calculation, you've already acknowledged that the galaxy that you're looking at is not part of the Hubble flow. So here's what you can do with that kind of idea. You can make this a representation of these galaxies all following the Hubble flow, so to speak, and then subtract out the kinematic part of this Sunyaev-Zeldovich effect, and then by subtracting out that kinematic effect, you basically just get this straight line, and then tell people that you've got a model that perfectly represents Hubble's value, except for this one little problem. Even the Sunyaev-Zeldovich effect is not capable of canceling out the because the thing is there's two Hubble flows. So I hope this doesn't screw up the sound on this animation, but I'm going to hit the play button on this, and you'll see what happened. Wait, did it go back far enough? It's not. It's supposed to go back further than that. Anyway, okay, we've got this blue Hubble flow, and then the red and the green Hubble flow start behind us. And you can see the blue Hubble flow, it's, in my opinion, it represents the outermost observations that we have, like the GNZ11. Some galaxies have a redshift of up to 11, so they're way out there, and they are like, there's one that's 31.9 billion years, 31.9 billion light years away. So I plugged 31.9 into this equation here. Then you've got let's say these red galaxies out here. They're going to be the galaxies where the Sunyaev-Zeldovich effect does not interfere with the motion of the galaxy, because they're outside of the Hubble distribution. And then the green dots represent the actual Hubble distribution, but there's red dots within the green distribution, and they would represent galaxies that are within the domain, within the area, within the sphere of the Hubble region, but they're going too fast. They've got a peculiar velocity within the Hubble sphere. Now here's a suspicious statement, because in Ethan Siegel's article, he says, as the errors went down, the central value stubbornly refused to change. Okay, so my question is, what do they mean the errors went down? Because let me talk about two different equations, two formulas. And you can see both formulas described here. One of them is called the standard error of a statistic, and the other one is called the standard deviation of the statistic. And the equation for the standard error is, I'm sorry, this is the standard error, the population standard error is equal to the population standard deviation over square root of n. And similarly, the sample standard deviation is equal to the sample standard deviation over the square root of n. So this is the one they should use, first of all. If they are doing standard error, actually they shouldn't use standard error at all. But if they did use standard error, then here's what would happen. Every time you add a new data point, your standard error is going to go down. So, for instance, let's look at this article. It says a large increase in the total number of type 1a supernovae, and find out maybe if they are using this number 1700 and dividing by the square root of 1700 to get their standard error. Okay, good news. The article is not behind a paywall, so I'm actually able to look at it. That's fun. First of all, searching the article for standard error produces 0 results. Also, searching the article for standard deviation also produces 0 results. So we can look at the abstract, which states that these analyses will measure W with 3% precision and H0 with 1 kilometer per second per megaparsec precision. Now, when they say this, precision, usually that probably refers to standard error rather than standard deviation. So by dividing by the square root of 1701, so they could take a standard deviation of 41.3. A standard deviation, that means a difference in standard deviation of 41.3 kilometers per second per megaparsec. Let's talk about that for a second. Okay, so we have this equation that says that the standard error is equal to the standard deviation divided by the square root of n. So they're telling us that the precision, which I'm pretty sure is the same thing as a standard error, is 1 kilometer per second per megaparsec. So we're going to multiply that by the square root of 1700 to get the actual standard deviation. The standard deviation then is 41.2. The square root of 1700 is 41.2 kilometers per second per megaparsec. So now, this is not going to be accurate. This is not going to produce a normal distribution because we've got a hard limit of, we are not going to get a 0 for Hubble's constant by any means. But if it were a normal distribution, the range from 1 standard deviation below the mean to 1 standard deviation above the mean would represent 68% of the data. If we assume that the mean is 70 kilometers per second per megaparsec, then we would have this range for 68% of the data. We would have 95% of the data under 152.4 and 99.7% of the data under 193.6. So bragging that by obtaining 1700 pieces of data that you have made your precision greater, you've somehow increased your precision, is only makes sense if you are absolutely certain that the quantity that you're actually measuring is a constant. In this case, though, there's no suggestion here that the actual quantity that we're measuring is a constant. It should be that the quantity that we're measuring is a property of that distant galaxy. And when the Hubble parameter is actually a property of the distant galaxy, it does not make any sense to um, talk about things in terms of standard error or precision. It makes more sense to talk about things as a matter of describe the distribution. So when Ethan says some fundamental assumption about our cosmological picture might be incorrect. Yes, absolutely. The assumption that Hubble's constant is something that you can get to, are the deviations between Hubble's constant can be eliminated by dividing the actual standard deviation by the square root of the number of measurements that you've made. This is a fallacy. um, this does not, this equation only works on values that truly are constants. If you're dealing with a value that is not a constant, this this representation of standard error is just absurd. But here we can see in this paper, because such objects are rare, approximately one per year, and their numbers limit the precision of the determination of H naught. So this is what they're doing. They're going to take whatever the standard deviation is and divide it by square root of their numbers. So that's what they're doing to get that precision down to a small, small number.